Good morning, everyone. I'm Haomiao, and I'm going to present our work titled Building Component Segmentation-oriented Indoor Localization using BIM-based synthetic data generation and deep learning. And I'm a master student from the University of New South Wales, and this is the author and co-authors. And this presentation consists of 6 parts. And first, let's move to the introduction. So indoor localization is critical for application like facility management, disaster response, and navigational assistance. So traditional methods include IMUs, Wi-Fi, or Bluetooth, but these methods often suffer from issues like the error accumulation, heavy dependence on the hardware, and the sensitivity to the environmental changes. And there's another method is the image-based positioning method, and it has the advantages of low hardware dependence, the discreteness, and reference position. However, the image method requires a lot of manual work for the dataset construction, and the effectiveness of the dataset will also change with the environment change. Although the previous BIM running method eliminated the need for the manual data collection, they also relied on the high level of detail of the BIM model and couldn't overcome the environmental changes. So we start to focus only on the fundamental building components like the doors or walls and some other components to reduce the reliance on the visual similarity with the BIM and overcome the environment changes. So the objective of this study is to develop and validate a thematic segmentation-based indoor localization method using the synthetic BIM generated images and deep learning techniques. It consists of it includes 3 parts. The first part is to automate the generation of synthetic semantic masks for both BIM rendered and view capture images, and to develop a thematic similarity metric based on the intersection over union. And the last one is to validate the feasibility of the approach through a case study and the low-level detailed BIM condition. So then it comes to the methodology. The proposed approach consists of 3 key stages, including the BIM-based synthetic image generation, the deep learning based image segmentation for view capture images, and the similarity-based image retrieval. In the first section, I'm going to present how we generate the BIM-based synthetic image. First, we focus only on the stable building components, which includes these 5 classes. And then we use Revit API to automate the user-defined virtual camera placement in the BIM model. These cameras are placed at user-defined intervals and with some customizable parameters like the height, resolution, and DPI. We assign a unique color to each component to generate the thematic masks. And we also apply a filter to retain mask with both floor and ceiling to enhance the quality of the database. And after that, the image segment, we select a image segmentation model, the ULO-8, which is trained using the HKU building dataset and focus only on the interior things. And we use this model to predict masks with the same 5 classes at the BIM generated masks. And the table is the training result of our model. And then it comes to the similarity-based image retrieval. The purpose of this section is to match the real image mask with the most similar synthetic BIM mask by the highest similarity score. And since IOU is a classic metric for measuring thematic segmentation, so we calculate the LU for each class to measure how well the real and synthetic masks overlap. And we assign different weights to different classes by their class importance. And we also conduct a case study in an institutional building at the University of Macau. We select a corridor area at the test bed, and it's about around 175 meters. And we placed 616 virtual cameras with an interval of 3 feet in the model of level of detail 200, and we finally obtained 1005 semantic masks after the filtering process at the offline database. And then it comes to the metric design. We select the baseline using the BIM rendered images and CNN features from the first block of the ResNet 50 to compute the similarity. And we have a system area of about 0.38 meters between the actual location and the nearest reference point. This is mainly due to the camera spacing configuration. And we use the top 10 range accuracy as the main evaluation metric. It combines a position score and a sequencing score to reflect the spatial accuracy and the retrieval sequencing accuracy. And the average matching accuracy of our study is 0.57, which is larger than the baseline method, which is 0.18. And the range accuracy may decrease when the multiple locations share highly similar visual features. And the first three measurement points, they include all these five building components achieve higher accuracy due to their rich semantic and spatial information. And the baselines low accuracy because of the visual mismatches between the simplified BIM rendering and real capture images. The implication of our study is this work process propose a BIM-based image localization approach that leverages thematic segmentation of fundamental building components, and it also offers strong adaptability to low-level detail models and environmental changes. But although this approach is currently in a proof of concept stage, it also demonstrates initial potential in terms of the feasibility and performance. But also we have some limitations, like the current camera settings are chosen empirically, and the current method is only use a single frame input, and we also struggles when different locations look structurally similar. So to overcome these limitations, we have some future works to do. First is to optimize the virtual camera setting and to use continuous measurements and probabilistic models. And we can also include some other building components like the firefighter equipments to make the difference between two images larger. And we can also test in diverse environments and software integration. And this is our reference list. And our study also acknowledged the support by these two fundings. Thank you.